Okay, questions to start with? Yeah.
Can we go over 30 from the back ones?
30 from the that are due?
Yeah.
We could do that after you turn them in.
Okay. I just know what you're doing.
I'm trying to remember what 30 looks like. It would probably be helpful. Here you go. So the thing about 30 is just generically when you're doing Newman projections, So when you look at these problems, and this isn't the exact problem. This isn't that exact one, but so the whole idea when you have two chiral centers is you're comparing you got to compare front to front, back to back. Are they both same, both opposite, one same, one opposite? So you have to always compare the two carbons, but in order to do that by either group switching or trying to rotate, they need to be in the same orientation. So the thing about 30 and also 29 is that the front carbon has the OH on it, and in the other molecule, the back carbon has the OH. So I have these two molecules, and they are not lined up with each other. So the front carbon in one is the back carbon in the other. If you're going to do a comparison, you've got to take one of the two molecules, and you basically have to, if it's oriented like this, you have to take it and flip it around. So in this case, we'd have to take this molecule and either flip it this way or flip it this way. So either flip it like this or flip it like this. And so either way we do that, so if I take this molecule and let's say I rotate it 180 degrees in the back, the front carbon is going to have this orientation because the down position there, and there, when I rotate the molecule around, that's going to put these three positions in the front. And then the back carbon is going to be up, down, to the left, and down to the right. So when I rotate this molecule, the back carbon, which is in red, will come forward, and the front carbon, which is in black, will go to the back. The two positions that won't change are the two methyl groups. So the methyl groups, one pointing up, one pointing down. The back carbon has the methyl group pointing down, it'll still be pointing down. The OH group, though, that was pointing up and to the right, when you rotate the molecule and bring the back carbon, the OH will still be up but to the left. And the hydrogen that is rotated is pointing to the back up and to the left will now be pointing in the front up and to the right. So all I did was just take this molecule and I just rotated it 180 degrees. For the front carbon that now becomes the back carbon, it's the same thing. The methyl group was pointed up in the front, it's still going to be pointed up in the back. But now the H that's pointing down and to the right will be down and to the left. The chlorine will be down and to the right, going from down to the left. So this molecule then is 180 degree rotation of this molecule, And so now we can compare those two molecules because the OHs are on the OH is on the front carbon, the chlorine's on the back, so they're now in the same orientation. So that's what you have to do with that molecule. Then if you wanted to, if we want to directly compare them, let's just come down here and let's rotate the front carbon up so the OH goes in the up position, the H goes down and to the right, and then the CH3 moves over to down to the left. So if I compare the front carbon on that molecule, is it the same or opposite of this one? So I got methyl group, OH, and H. So the front carbon is the same. So the front carbon is the same. And now we have to do the same thing for the back carbon. So rotating chlorine down, so it's here, rotating the H, so it's up here, and rotating the CH3, so that's there. So all I'm doing is just rotating. I'm rotating the front carbon here, 60 degrees, and I'm rotating the back carbon 60 degrees to put it in this orientation. Now the back carbon, front same or opposite? It's oriented now H to H, CH3 to CH3, Cl to Cl. So the back carbon's the same. So if the front carbon's the same, back carbon's the same, they are the same, not meso. So they're same and not meso. And why can't this molecule be meso? Because there's an OH, a CH3, and an H. On the front carbon, a CH3, an H, and a Cl. The front and back carbon do not have the same three groups attached. A meso-Newman projection would look like this. If you can put the molecule into that, that is a meso-Newman projection. But if the front carbon and the back carbon don't have exactly the same three groups attached, it can't be meso. The same thing's true for a Fischer projection. A meso would have to have the same three groups attached to it, and you'd have to be able to write the mirror plane like that. So this would be a meso Fischer projection. If you don't have the same three groups attached to each carbon, it can't be meso.
Instead of doing it that way, could you just draw the picture the Lewis structure with a dash?
You could take this molecule and you could realize that it looks like this, and then say, okay, the left is the front carbon, so the OH would go here, the Cl would go there. My perspective on this is I'm going to be over here, looking at the molecule that way. So that means on the front carbon, the hydrogen is going to be bold, and the CH3 is going to be bold, and then the CH3 on the front carbon is going to be back, and the hydrogen is going to be back here. So you could do that, and then for this one, if you do that, just realize the left carbons aren't matched. So if you do that for this one down here, it would still, then it's going to look like this. So that the CH3 is down, the H is bold, the Cl is bold, that's a CH3. Wait, CH3 is up here, Cl is down here. And then H and OH. No, OH. Yeah. OH there, and then What is that? That's an H. So then it would look like that. Except it wouldn't look like that, would it? Sorry. From the front perspective, I got the carbons messed up. Okay. From the front perspective, the CH3 would be down. Oh, what am I doing? I was writing the Newman projection of this after I'd already rotated it. Writing the Newman projection on the one that hasn't been rotated. So in other words, not this one, but this one, it would look like, it would be in the same orientation. The CH3 would be up, the chlorine would be bold, the hydrogen back, the OH bold, the hydrogen back, and the CH3. So you would be comparing this one to this one. Again, left carbons aren't matched, right carbons aren't matched, so you'd have to take this molecule and rotate it around if you wanted to do same or opposite. You can always do R and S on this molecule since it's not polar, or since it's not Mezzo. But you just have to remember you're comparing this carbon to this carbon and then the right carbon to the left carbon. So you could do R and S and see if they were the same or opposite configurations.
Okay, I'm a little confused because I watched one of your videos and it said, so if you have like your Newman projection and you want to figure out R and S, like it said to convert to the, not the staggered, but the eclipsed conformation and then put it into the Fischer.
You can do that if you want.
Okay.
So this is just another way. This is just another way of doing that. Ultimately, you got to compare the two carbons. Are they the same in both cases, opposite, one of each? So yes, you could put this into a Fischer projection. Putting it into a Fischer projection would require putting it into this eclipsed, looking at it from underneath so that if I had A, B, C, D, E, and F, looking at it, B would be here, E would be here, and then A, C, D, F. So you could look at it from underneath and you could put it into a Fischer and then make the comparisons. But in those two cases, your top carbon is going to be different, is going to be in the top in one, in the bottom in the other, so you're going to have to at least rotate it and line them up. Unless you do RS. But then you got to make sure you're comparing the right carbons doing R and S. So you can do an R and S. It's going to be longer, but you could do R and S for any molecules that aren't Mezzo. Because if they're Mezzo, R and S breaks down. So yeah, there's a video on how to convert this into a Newman. I think there's the other video is how to convert this into something that looks like this. Either one, whichever one you can do that. What else? And I have a question. of these three, A, B, and C, which one of those reacts with hydroxide the fastest? If you had to rank those, how would you rank them from the ones that react, the one that reacts the fastest to the slowest? I'll give you a minute to think about it. And then I'm going to ask. And if you need a card, because you have misplaced yours, I believe I have a couple here. Okay, everybody got an answers or got rankings? Question number 1. So which one of these reacts the slowest? Don't anticipate my question right off the bat. So which of these, I want to go slowest to fastest. So which one of these reacts the slowest? A, B, or C? Or D, don't know. Does everybody have a card? Anybody need a card? I still have one card. Do you know how to use these?
Yeah, I have one in my door, but I forgot.
Okay, well, it's not doing any good there. Okay, everybody else got a card? All right, ready? Okay, let's see what we have. We have 17. Oh, we're all over the board. We've got 17 A's. We've got 4 B's. We've got 5 C's. And we have 3 D's. So, let's do which one reacts fastest. So let's So which one is going to react fastest? I won't tell you which one is the correct answer there. You can assume that the majority is right, although that would be an assumption. Okay, which one reacts the fastest? Okay. I've got fastest, I've got 1A, 8 B's, 20 C's, and 1, I don't know. So somewhere between slowest and fastest, we got rid of a couple of don't knows. Okay. So how do we rank alkyl halides in an SN2 reaction? How do we rank them according to their reactivity? What do we use? What are we using to base this on? As you made your rankings, what was the criteria you were using? Give me an answer. The number of carbons, what do you mean number of carbons? The amount of molecules in the chain. Okay. And B had 5. And and A had 6. Okay. Anybody use another criteria? Why did you choose A being? Why did 17 people choose A being the slowest? No, it's actually a cyclohexyl. If it was an aryl, I would agree it's slowest because it's not going to react at all. But it'd have to have double bonds for that. So it's just a cyclohexyl. Okay. Sticks. Petra, why did you rank them the way you did? What was your criteria? Okay. That's fine. Emma Workman.
For which one the slowest or the fastest?
What criteria did you use to rank them?
I went off of primary, secondary, and the tertiary ranking.
Okay, primary and secondary and tertiary, what carbon were you looking at to make those criteria?
The one closest to the bromide.
The one attached to the bromide?
Yeah.
Okay, and this one? And this one? Okay. Emily, what was your criteria? Oh, you already know your criteria. It was number of carbons. That'll save you. Benjamin.
I was also one of the I don't knows, but
Okay.
I was kind of looking at the structure of it, like how attached the carbons were to one another. Like in the cyclohexane, there's carbons attached to them, right? So I guess I was looking at the primary and secondary carbons on them.
Of the carbon that's attached to the bromine.
Yeah.
Okay. Viola.
I also got the number of carbons too.
The total number of carbons. Okay.
I mean, generally, I wasn't super sure, but I was right for both of them. I'm not really sure why, but my criteria was like complexity of the molecule it was attached to. I just feel like it would be easier for the nucleophile to attack if there was like less going on.
Okay.
I looked at the steric hindrance, like how big the molecule was, kind of like what you were saying, how it could attack a less complex molecule.
I also have a question. Is this the electrophile? Like what
Yes.
are these molecules? Okay.
These are all the alkyl halides. These are all the electrophiles. All these carbons attached to bromines are slightly positive because they have given up some of their electron density to the bromines that are slightly negative. And so in each one of these cases, the hydroxide is going to come in and attack that carbon and kick off the bromine. And so that's the basis of our SN2 reaction. The hydroxide is going to come in, attack that carbon, and kick off the bromine. Or it's going to come in, attack that carbon, kick off the bromine. Okay. Anybody want to add? So, I get the, what's going on with the molecule. Like there's a lot going on versus there's not a lot going on. Usually, I had a student over the summertime who would have said, well, she's got a lot going on. Versus the other one where she doesn't have a lot going on. I am not hip and cool anymore, if I ever was. But what a lot going on, steric hindrance. And since these are the carbons that are the nucleophile is going to come in and attack, remember what the mechanism of this reaction would be. So it is SN2, which means the hydroxide is going to come in and it's going to attack the carbon attached to the leaving group, which in this case is the halogen. It's going to kick off the leaving, and then it's going to go into this transition state, where there's going to be delta minus charges on both the nucleophile and the leaving group for the moment. So it's going to go into this transition state, and then when the bromide leaves, in this case, we're going to end up then forming our O carbon bond. So if all the leaving groups weren't the same, and the nucleophile wasn't the same in each case, we might get into our discussion from last Wednesday about strength of nucleophile, strength of leaving group, but in this case they're all the same. So the issue is, how does the structure of the alkyl halide, which is the electrophile, because in each case this carbon is slightly positive, so that's the electron-rich or electron-poor species that the nucleophile is giving to. So what's going to prevent the hydroxide from adding to that carbon? A lot of steric hindrance, which is the complexity of the molecule. Now, it just so happens that in this case, the way I wrote them, I gave the fastest one the less number of carbons, and the slowest one happened to have the most number of carbons. It's not so much the total number of carbons, it's the total number of carbons that are attached to the carbons attached to the leaving group. And whether or not that carbon is, in this case, primary versus, in this case, secondary. So it's all about steric hindrance. The steric hindrance is going to prevent the hydroxide from approaching that carbon and forming the bond. And if we sort of remember last Wednesday, what we talked about was the idea that in this transition state, what's really happening is the hydroxide is taking its lone pair in a hybrid orbital, and it wants to overlap it with the little teeny tiny orbital of the sp3 hybrid orbital. And that's going to get us to the transition state. So we can think about how much steric hindrance there is around that carbon. And in the textbook, there are some pictures where they make it bigger and bigger to show you the difficulty in the nucleophile getting to a carbon when there's a lot of steric hindrance around it. In the video that I have in last Wednesday's folder, there is a picture where the nucleophile, if you're looking down on that carbon, looking down for the backside attack, if there's a lot of other groups around that, you're going to have a hard time getting there. Now, that's not the technical answer, but we can think about that. Okay, that's the a lot going on portion, steric hindrance. Now, what the true technical answer to this is, it has to do with energy. Okay. And so in chemistry, energy is what makes reactions occur or not occur. Energy is what's going to make them occur faster or slower. That's the currency in chemistry. You want to know why something happens, you need to go into the energy. Right? In politics, you want to know why something happens, you need to look at the money or the power. Okay? Chemistry is just totally based on energy. So if you think about putting a lot of steric hindrance into that reaction, first of all, here is a reaction coordinate diagram for an SN2 reaction. We have our transition state, which is this trigonal bipyramidal transition state. We have the difference between the reactant and the transition state. That's our activation energy. And then we have to remember that the rate is equal to A e to the minus EA over RT, which is called the Arrhenius equation. And in the Arrhenius equation, that gives you the relationship between rate and activation energy and rate and temperature, which everybody remembers, right? The reaction, if the activation energy gets larger, what happens to the rate? It decreases. If the temperature goes up, the reaction rate increases, right? But this is what controls that. That's the mathematics of it. So what happens is that if you have a lot of groups around here, if you have a lot of steric hindrance, what's going to happen is that's going to raise the energy of the transition state, which is going to make the reaction go slower, or if the transition state energy gets too high, you're not going to have a reaction because you can't overcome that barrier. And that's exactly what happens with what kind of alkyl halide? Primaries will react faster than secondaries because there's less steric hindrance. What about tertiaries? What happens to a tertiary alkyl halide in SN2? Can a tertiary halide undergo an SN2 reaction? No. Right? No. So if I'm ranking these methyls, when you just have a methyl group attached to a halogen, that's going to react the fastest, then primaries, then secondaries, then tertiaries, because tertiaries don't react in an SN2 mechanism. So it's all based on steric hindrance. But that steric hindrance, really, the true answer is it's about the activation energy changing as a function of the transition state changing. Or there's just a lot of steric hindrance.
So back to like our first question, since the like B and C were both primary or they're like tied.
Well, that's true. So both B and C were primary, which would make them tied. So now let's look at exactly what you said. Now let's look at the groups that are attached to those primary carbons. And which one has the greater steric hindrance? Or which one has the less steric hindrance, if you want to look at it that way. The one with the greater steric hindrance is what? Ethyl group versus tertiary group. Which one's more sterically hindered? The tertiary, and so that's why in this case, B would have been in the middle because it's primary first and then secondary after that. Now you could probably make an argument that maybe B and A might be flipped. We'd have to do the experiment to figure that out. But for the most part, we go primary, fastest, then secondary. And so in this case, we would look at those being primary. So we're again looking at steric hindrance as the basis for the reactivity. So fastest, C. Slowest, A. So if I'm looking at that, I'm saying, oh, well, most people were able to answer that question correctly. But are we all kind of on the same page as to why that's the case? So for an SN2 reaction, there are 4 key elements to an SN2 reaction. Okay. The 4 key elements are, number 1, the rate equation. Number 2, the fact that it is a one-step concerted mechanism with a trigonal bipyramidal transition state. That's what the double dagger thing is a transition state. When it's small like that. When it's big and it has things attached to it, it's a Fischer projection. But when it's small like that, it's a transition state. Number 3, when you react a chiral molecule, when a chiral molecule reacts in an SN2 reaction, what happens? And then 4, the rate is methyl, primary, secondary, tertiary, not reacting for the SN2.
So what does that mean?
Well, let's deal with the rate equation first. Let's just finish this table out. So what is the rate equation for a primary, what's the rate equation for an SN2 reaction? The rate equals K times concentration of the alkyl halide and the concentration of nucleophile to what power? To the first power each. What does that mean? If I doubled the concentration of the alkyl halide, what would happen to the rate? It would double. If I doubled the concentration of the nucleophile, what would happen? The rate would double as well. It also means that not only is the nucleophile, the rate of the reaction is dependent on the strength of the nucleophile and concentration, it is also dependent on the strength of the leaving group, since the leaving group is in the mechanism and it's in the rate equation. So I can make an SN2 reaction go faster by using a better leaving group. So all of these, the nucleophile, the alkyl halide, the leaving group, they're all playing a role in the rate of the reaction. Stronger nucleophile, faster reaction. Better leaving group, faster reaction. Increasing concentrations of either, faster reaction. Because what's going on in the rate determining step, since there is only one step of the mechanism, which is the one we wrote here, this is our mechanism, all three components are in there. And so they all affect the rate of the reaction. So that's what the rate equation, that's the role the rate equation plays. Now, what about a chiral halide? If I started with a chiral halide that had something like a CH3, an H, and then an ethyl group, and I reacted this with hydroxide, I have two questions. Well, really, I just have one question, but we'll break it up into two. If I start with just this enantiomer, the molecule solution is chiral. Okay. Will the product, overall product of this reaction be chiral? Will it rotate plane polarized light? The real question is, how many products do I get out of this reaction? Do I get one or two? Is the product chiral? Well, my mechanism says my hydroxide comes in and it reacts from the backside and kicks off the bromine. So I'm going to go ahead and write the transition state out, as you will have to. When I write the transition state out, I'm going to have the groups attached to whatever bond they were attached to. The CH3 is going to still be attached to one in the plane. The bold wedge is going to be attached to the ethyl group, and the dashed wedge is going to have the hydrogen. And I put a skeleton around the dashed wedge so it looks like a dashed wedge as opposed to dotted lines. Delta minus charge, transition state. What happens to the final product? The final product will now look like this. When the hydroxide kicks out the leaving group. What I could have done is I could have asked you and said, what is the product stereochemistry? So if we didn't have the product, if we didn't have all of this stuff, my hand is covering up the last two parts, which I can't do without throwing myself over the screen or getting that box bigger. If I just would have given you the molecule to begin with and said, what is the stereochemistry of the final product? I would have given you three choices. I would have given you R, S, 50-50, R and S. So what is the stereochemistry of the final product? And what was the stereochemistry of the reactant? So for the reactant, what's group number 1 over here? What's group number 1? Bromine, number 4. Number 2, ethyl. Number 3, methyl. Is 4 pointing away from me? Yes. So going from 1 to 2 to 3 is what? Clockwise, so this is R. How about the final product? What's the number 1 group? Hydroxide, number 4. Hydrogen, number 2. Ethyl, number 3. Methyl, 4 pointing away from me? Yes. Going from 1 to 2 to 3 is now what? Counterclockwise, and so it's S. So when you do an SN2 reaction, if you have a chiral molecule, its configuration will be inverted. So this is called the inversion of configuration. Not only do you get a chiral molecule because the product that you make has a chiral center and it's not 50-50, you get the inversion of that configuration. R becomes S and S becomes R. Okay. So those are the 4 key elements of SN2. There are solvent effects that will play with this. There are strength of nucleophile, strength of leaving group effects that will be involved in this. But these are the 4 essential elements of SN2. Which means that for today, there are 4 essential elements of SN1. The first of which being the rate equation. So I'm just going to start out by saying here's the generic reaction that we do whenever we do substitution. We react our nucleophile with an alkyl halide. The nucleophile replaces the alkyl halide, the halogen, and we get the substitution product. Now, I can imagine that when people were looking at these reactions, they decided to take something like hydroxide and react it with like the different butyl groups. And so maybe they reacted at first with butyl bromide. And then they reacted it with a secondary butyl bromide. And then they reacted it with a tertiary butyl bromide. And they found out that they got substitution product no matter whether they used primary, secondary, or tertiary, although it's questionable whether they would have known about primary, secondary, or tertiary to begin with. But let's assume they did. So they did these reactions. All 3 of them undergo substitution. They measure the rates. They find that primary and secondary, they get the rate equals K times concentration of halide to the first times concentration of nucleophile to the first. They go to the tertiary and they measure rate as a function of alkyl halide concentration and nucleophile concentration. They start with 1 molar each, and they find out that the rate was 10. And then they double the concentration of the alkyl halide, and what happens to the rate? They found it doubled. And they're like, oh, great. So for tertiary halide, it's rate of the concentration of the halide to the first power. Then they hold the concentration of the alkyl halide constant, and they double the concentration of the nucleophile, and the rate didn't change. And they probably did that more than once. And then they said, well, let's triple the concentration of the nucleophile. And what did they find? The rate still didn't change. So the concentration of the nucleophile to the 0 power, because anything to the 0 power is 1. So this reaction isn't dependent on the concentration of the nucleophile. Right? So then they're like, I'm sure they sighed. Because now we have to figure out a new mechanism. Because whenever your kinetics changes, that means that your mechanism changed. So then they had to go about trying to figure out what's this new mechanism. And there was no one person that did it, or else it would have a name. It doesn't have a name associated with it. There's no Dr. SN. That's just nucleophilic substitution. So then they had to develop the mechanism from there, which is in the video in the folder for today. If you've watched that video, you know the rest of the story. If you haven't watched the video, I would strongly recommend you do that. Or read the textbook. I think one of the reasons why I put the videos in is so that you can get a chance to look at them either before or after reading the book. It depends on your style. If you can read the book and everything's fine, you may not need the video, but for the most part, you might need the video and then go back to the book. So what I would like you to do for Wednesday is go back, and if you haven't done that for SN1 and SN2, please do that. There is a video in the Wednesday on solvent effects, I believe. And I know for the second part, it's how do you know whether something is SN1 or SN2? And I developed the chart. So take a look at that. Basically, the next lectures and as we move into chapter 8 and 9 and 10 are all going to be going back through SN1, SN2. There's also this thing called E1 and E2 that we need to talk about, and that we'll start talking about on Friday. But we need to talk about solvent effects, which I've already done a little bit in the Piazza videos. And if you haven't taken a look through the Piazza videos and looked at those questions, you might want to do that, because I do spend some time recording and answering people's questions on book problems as well as just questions that people ask. So some of that is in there. It's also in the 221 section of the YouTube page, but you can get at them through Piazza. Okay. So if you have any questions on Wednesday, bring them to class on Wednesday. I'll answer whatever questions. We'll talk about solvent effects. I will also have some practice problems because you need to be able to write the mechanisms of SN1 and SN2. And so if there's something about the mechanism of SN1, bring it, anything like that. Ask on Piazza, or bring it to class and we will go over it, okay? I will take your Scantrons and I will give those back to you on Wednesday.